Now we are heading towards the next functions, that's complex sinusoids. A complex sinusoid is a special case of complex exponential. That is, you can see here, that is a lambda. If the lambda has a complex value, so that will be a complex sinusoid. That means you can see here that if lambda is a real value, that means real part of the lambda is 0. If a is a complex value, that means whether a is complex and lambda is purely imaginary, so that will be a complex sinusoid. So it is a function of the same form, but the lambda will be the j omega. So a is complex and omega is real in that part. By expressing a in polar forms, that means a j theta part, that means a e to the power j theta parts terms, and using Euler's relation, we can rewrite xt as xt equal to a cos omega t plus theta plus j a sin omega t plus theta, that means the imaginary part, that is the real part. And thus real x and imaginary x are the same except for a time shift. Also x is periodic, and fundamental period t is equal to twice by omega, and fundamental period frequency is omega, same as that. Now coming back to the again another point, that is the complex sinusoid graph. Now these sinusoids are quite similar to that, but these graphs are similar to the graphs that we have take to the normal sinusoids, but they have some negative values. There's some other conjugate values out there. So that is one of the basic components of what that is complex sinusoids. Largely the general complex exponentials. What are the general complex exponentials? Here you can see in the most general case of a complex exponential, that is the basic complex exponential, and for that there is a polar form, and the lambda should have to be sigma plus j omega. In that particular situation, there is a real part and the imaginary part of the same as before, and the real and imaginary part such each product of the real exponential and real sinusoid. One of three distinct modes of the behavior is exhibited by xt, and depending on the value of sigma, that means if sigma is equal to 0, that means it's a real sinusoid kind of complex sinusoid, and if the sigma is greater than 0, then that will be a product of the real sinusoid and a growing real exponential, that means the growing exponential. And if sigma is less than 0, then that will be a decaying real exponential. So that is the difference when we have the different value of sigma are on the cards and are on the facts. Now we can see some general complex exponentials. So these complex exponentials are not only dependent on the e to the power j omega t, they are depending on the real values too. That means if the both values, that means the value of the amplitude and the value of the theta, that means the phase delay, these two parts are both are the complex exponential, so we have this kind of thing. So if it is sigma is equal to 0, then that will be a quite real type of sinusoids, but there are three mode of behavior. If it's greater than 0, so that is a two that you can see there is increasing part of increasing exponential part, and under this the sinusoid just runs through. That means that is the increasing type of exponential out there. That means that is the trending is quite this exponential trending is quite upwards, and if it's decaying, that is downwards, that has been lambda is less than 0, that means that has been upgraded through to the negative part of the x-axis. So that's now for the general complex exponentials. Now we are heading towards the next function, that is the relationship between complex exponentials and real sinusoids. As you can see here, if we use certain kind of a to e to the power j omega t, and you know e to the power j omega t, if you just construct the e to the power j omega t as Euler's relation, that means cos omega t plus j sin omega t, and that a has been multiplied to each other as the commutative theory. Moreover, a real sinusoid can be expressed as the sum of two complex sinusoids using the identities, that means a cos omega t plus theta is equal to a by 2 e to the power j omega t plus theta plus e to the power minus j omega t plus theta, and that is a sin omega t plus theta is equal to a by 4 2j e to the power j omega t plus theta minus e to the power j omega t plus theta. Note that above we are simply restating results from the material and complex analysis. Now we are heading towards the unit step function that you have to know, that is the Heaviside function known as the Heaviside function. That is the condition of a unit step function. Whenever you get t is 0 from any kind of positive value, that will be 1, and otherwise it will be 0. Let's look like a step. That means you can see the staircase type. That means whenever you use a staircase, or you use staircases to hold in get up to the one floor to another floor, that's the thing. That's the step by step. We know this word. And the unit step function means all kind of positive numbers including 0, that is the unit step. If the value is 1, that's unit. If that's the value 1 means unit, that's unit step, and that has been denoted by ut. Whenever you see ut, the function has these conditions right there. So due to the manner in which u is used in practice, the actual value of u is 0 is unimportant. Sometimes values of 0 and half are also used for u0. A plot is function is shown below. That means if it is 0, that you can get 1, but otherwise in each and every type of values you will get 0. Now you can see the graph below. That is quite look like a staircase or step. Now the Signum function comes forward. The Signum function is one kind of a function that is like that you can say that is quite similar to the unit step, but has a different type of figure. That you can see the Signum function denoted SGN function. Whenever you see this kind of function, that is SGNT, that will be definitely a Signum function. And whatever greater than 0, that means whatever positive numbers, you will get 1. Whatever the negative numbers, it will be minus 1. That is the y-axis, minus 1 in the negative section, plus 1 in the positive section. From its definition, one can see that the Signum function simply computes the sign of a number. That means Signum is named for the sign. You can just utter or pronounce this function as Signum function. Function. That means that depends on the sign of the number, the x number, the t number. If the sign is positive, that will be positive 1. If the sign is negative, that is negative 1. But in 0, that will be no value on that function. So that is the Signum function. Now we are heading towards the next function, that is the rectangular function, and it is a very much popular function. And this function, the rectangular function, also known as the unit rectangular pulse function. That is a one kind of pulse. Here you can see there is a pulse. There is a pulse. In that fashion we use a pulse. And due to the manner in which the rectangular function, that is denoted as a rect t, from minus half to plus half, that means the pulse has been divided into two parts, minus half, 0 to minus half, and plus 2 0 to plus half. That means minus half to plus half, it is 1. It has a constant value of 1 under that, and otherwise it is 0. So that is the function condition. Due to the manner in which the rectangular function is used in practice, the actual value of rectangular t at t is equal to plus minus half is unimportant. Sometimes different values are used from those specified above. A plot of this function is shown below. Now we are coming back to the triangular function, the most important function of the unit triangular functions. The triangular function or unit triangular function is denoted by TRIT, and the function value is like that. It is a slope type of function, the just a positive slope and negative slope function. That the positive side positive slope and the negative slope, and the slope is 1 minus 2d. It is a function of what can I say, a linear function, straight line function. 2 is the slope of the function, so that will be minus half to plus half is the main region, similar to the rectangular, but difference in the y section, that is slope. plus of and minus of slope.